processes. I mean, you should be able to appreciate what we talk about going on here, that we're cleaving it in half, we're making ATP, we're doing some oxidation. You can see that here. That's the part really I want you to focus on, not just memorizing the structures of the names. Okay, but here we're investing some energy. We're putting a phosphate on the glucose. So there's glucose. We put that P circle stands for phosphate, PO3 group has been added. So the enzyme hexokinase does that. Here's an isomerase. Remember, isomerase is one of the classes of enzymes that converts different isomers. We're going from a glucose to a fructose. So rings changing to 5-membered ring. Then we put on another phosphate with another kinase. Spend another ATP to get a doubly phosphorylated molecule. And then we do the cleavage with an enzyme called aldolase. It breaks it into these two fragments. This is the one that will move forward. The glyceraldehyde 3-phosphate moves forward. There's an enzyme that triose phosphate isomerase that will interconvert these. So we make one of each, but then in the next step, this guy gets converted into that, and the pool of glyceraldehyde 3-phosphate moves forward in the next step. So far we've just spent energy. We haven't made any. This aldehyde fragment, here's the aldehyde group, gets oxidized to the level of a carboxylic acid. So instead of CO double bond O2 and an H here, we have a COO, not an H. It's a anhydride, phosphoanhydride of a carboxylic acid. So we've done the aldehyde carboxylic acid step. That takes 2 electrons, oxidation. We part those electrons on NAD, make NADH. Where does the phosphate come? This is different from before. Instead of ATP donating the phosphate, it's just simple inorganic phosphate from solution being added on to the carboxylic acid. This makes this a high energy phosphate, this oxidation step. And this is where substrate level phosphorylation comes in. This has sufficient Gibbs-free energy. It's higher in energy than ATP. It's sufficiently high in energy that it can donate its phosphate successfully to ATP to make ATP. And that's an energy, even though you're making ATP, this is energetically downhill. It's a favorable conversion. Because this is just such high energy. So we started out with 2 phosphates. We donate 1 to ATP. We still have 1 phosphate left. We do some rearranging to make this next to last intermediate here, phosphoenolpyruvate, another very high energy molecule, much higher energy than ATP. And again, it's high enough energy to donate its phosphate to ADP in the second step of substrate level phosphorylation. And what you're left with then is pyruvate. The so-called payoff phase is this step. You're paying off because you're generating a couple ATPs there, a couple there. Remember, the stoichiometry here is per glucose. At each enzyme catalysis, you'll make just 1 ATP, but you're going to do this twice for each glucose molecule. So this kind of summarizes it. Glucose, you spend a couple ATPs to set up some high energy compounds in the first phase, and then the second phase, you generate ATPs. Spend 2 here, get back 4, so we have a net of 2. We're also oxidizing 2 molecules, so we get 2 NADHs, and we get 2 pyruvates. That's glycolysis.